Right.
We're on.
So perfect. All right. So Chris, um, I wanted to set this up because I have a question for you. We we're always talking about power factor. Power
Constantly.
factor is a constantly. I mean,
As electricians, it just comes up all the time.
my wife was just like, "Hey, power factor," and I was like, "Yeah."
Yeah. We just talked about, yeah, it just came up at dinner the other night with the wife too. Yeah.
Yeah, yeah, it's crazy how this happens. So, so, so I'm tired of her constant nagging me about power factor.
Right.
Yeah, and I'm wondering if we could put this to bed, just
That works.
just be done with it. Uh, yeah. So with that aside, in all seriousness, I know there's power factors uh, is a percentage in certain questions that we have for our electrical licenses and things of that nature. And I don't think that it's really truly understood. I've taken a couple classes, and when you have to use power factor, the explanation is just use this decimal point here. And if you really want to look at power factor, you're going to have to figure it out on your own.
Hmm.
So, or go to school and be an engineer. So I was thinking this might be a good way for us to go over it and get the difference here. So what we have up on our screen is the difference between apparent power and reactive power and true power. So where do we
Hmm.
start this conversation? So I am a first, I'm a first or second year apprentice. Apparent,
It's your, yeah, you're usually better at explaining this, but unfortunately, uh, most of this is best explained mathematically, right? So we can look at some right triangle math because we know, depending where apprentices or students are at in their studies, that leading and lagging effect of voltage and current when there's inductive and capacitive components, right, or reactive components, that the farthest voltage and current can be out of phase with one another is 90 degrees. So that just works out. We can use Pythagorean theorem. Or, like here, we're going to add things vectorially. So best explained mathematically, but then you have the best analogies and stuff and kind of bring it back to earth. But uh, I think the next slide basically explains apparent power the best. Was it the next slide?
yep,
Yeah, there it is. So apparent power, like the slide says, is basically I get my voltmeter and I know that my source or applied voltage is 240 volts. And I see that I've got a resistive load and an inductive load in series. And when I look at my line current, it's 4.8 amps. So that's the apparent power. Apparent because if I took actual measuring instruments, then that would be the product of 240 volts times 4.8 amps. So 240 volts applied, 4.8 amps of line or total current flowing in this series circuit. That's the apparent power. But now you and I know, is that really, are we getting so much true power out of this circuit? Probably not. So true power on the left is the result when voltage and current are in phase with each other. So even though every AC circuit has some inductance, some capacitance just naturally going to happen, it's usually negligible, it's ignored. So if we've got uh, the incandescent lamp, for example, then across the load, there's no funny business. Voltage and current stay in phase with each other again, mathematically explained. On the next slide, we can go a little further into detail, but when both voltage and current are in either the positive or negative side of that sine wave, running along that horizontal time axis, the product is true power. Now you get leading and lagging, like what's on the right. Again, and not all the times are voltage and current both either in the positive or the negative. So at times where maybe voltage is in the negative and current's in the positive, that's when you typically explain if you're 90 degrees out of phase, like in this inductive circuit there on the right, uh, the inductor's returning power to the source, right? So in that form of that collapsing magnetic field and counter electromotive force. So,
So here's the way I'm looking at it. We're talking about RLC circuits all the time, right? So if I
mm-hmm,
have so what I have maybe right here would be a picture of a light bulb, an incandescent old school 1992 light bulb
mm-hmm,
where my current is almost in phase with my voltage. It's just that I'm not going to have 120 amps and 120 volts at the same time, right? So there I am. But if I have a resistive or capacitive X of L or X of C,
mm-hmm.
this is kind of
There's,
where I'm at with it, right?
yeah, yeah. If you've got X of L and X of C, most likely it won't be at 90 degrees out of phase, but somewhere in between 0 to 90. But yeah, on the right would be like a high intensity discharge lamp, right? So metal halide, whatever, high pressure sodium, whatever it may be. But now you've got reactive components, and voltage and current are gonna get a little out of phase with each other here.
Okay. All right. So my voltage and current getting out of phase. Explain the difference between the X of L, the X of C, and when we're talking about VARs, right?
Mm-hmm.
So I've got current leading or lagging. That's more an issue of my impedance, right? In this picture.
Uh, so impedance is just a measurement of total opposition to current flow where you have reactive components in addition to resistive components.
So I could say
Uh,
Z is equal to resistive components being resistance X of L and X of C.
yeah, and all of those are measured in ohms. But yeah, if you had, R, if you had a true resistor, you're just going across the filament of like a tungsten filament lamp. And if you had some inductance across the motor winding, and if you had a capacitive bank for whatever power factor correction, or maybe you've got some capacitors in parallel just to get the desired output voltage, just to ignite some gases in like a neon, you know, uh, lamp or some other high intensity discharge lamp.
So let me
So
throw a
you could,
curveball at you.
yeah,
So my mother, because I'm telling you, these girls they're always asking about power factor and stuff, right? So
yeah, I know.
my mom said that Elon Musk was selling this device that I could plug into my wall, and I could save 90% of my power. Has anyone asked you about this yet?
No,
You don't
I would
know?
be curious too. But now I do know, like a lot of today's inverters, taking whatever a photovoltaic source. I know Tesla has inverters that many of those can introduce reactive powers into the grid, those that are utility interactive to help actually uh, correct power factor like for the utility. So
Right. So
maybe something like that.
it was it was a legitimate thing. They're advertising this thing that you can plug into your home, and it will clean up your power, and you will save 90% on your bill.
And
That's
that's beyond me. I just usually say that's the wizardry of electronics.
that
That
that is what I think I looked it up. It's called Hokum. If
okay.
you want to save 90% on your bill, turn off 90% of your consumption.
Well, and that I mean, yeah, that alone that just sounds like a load shed thing. I mean,
Yeah,
no one
it's
goes, I don't unplug my computers at night. I don't unplug my TV. I don't unplug my, streaming devices. All of those things are consuming a little bit of energy, even though they're plugged into the wall. But now, you know, power factor correction, right? Or you look at a power study analysis and what they're doing. I don't think we'll get that into depth, but basically, um, when we teach the apprenticeship, often people go, this is, you know, your first year studies would be DC circuit analysis, but we're showing it there on the left could be AC circuit too, that if you only have tungsten filament lamps, well, like lamps, true power, basically the product of the volts times the amps is equal at every component. Well, when you start to throw in reactive components, it doesn't work out that way. So basically, you put in more power than what you're getting out. So across the tungsten filament lamp, if you put in 100 watts of power to a 100-watt incandescent lamp, you get 100 watts out, right? So you put in that 100 watts of electric energy and you get 100 watts out of heat and light, or, lumens from that lamp. So it's 1-to-1. There's no ATM fee, and everybody's happy. And for most of us in a house, uh, maybe you care, but most of us don't, because it doesn't affect our billing like it does for a commercial customer. And when they're how they're metered for their power consumption turns from kilowatt hour to kVA hour.
Right. So I like the beer analogy.
Mm,
KW would be the liquid beer that you have, and the KVA is the foam and the beer. So if
mm-hmm,
I go to the ball game and I pay $140 for my bottle of beer, my glass of beer, and a paper cup, that $140 covers the foam and the beer.
mm-hmm.
Doesn't matter how much foam. So if I could reduce the foam, then I get more for my $140 beer.
Yeah,
Okay, and with inflation, it might be at 150 now. I haven't been to
but
the ballpark this year.
I think that's pretty accurate. But that's
Okay,
what it costs, right?
I think so. Yeah.
Regardless of how much foam is there or apparent power being the total class, there's going to be some foam, but the cost is the cost. So, and I don't know if the next slide breaks down like this would be a nice representation of what we call quadrature power or wattless power. So, what's going on here? Not sure if we've got inductive or capacitive. Uh, where's my voltage? Where's my current? What's leading? What's lagging?
My current looks like it's leading. So if I use Eli the Iceman,
Oh, this would be a pure inductive with the voltage leading, right? Looks like voltage is leading. But again, so the analogy I use here is I always like to use regifting. Uh, so Seinfeld fans, Label Baby Jr., or what was the other movie I like to refer to for the regifting? Old School, right? Luke Wilson gives Will Ferrell the bread maker, and then he gives it right back. Later on, at his wedding, Will Ferrell tries to give it back to him. But no one ever benefits from the label maker or the bread maker. It just continues to exchange hands. No one ever uses it. So that's kind of how it is here. So we see voltage and current. One's in the positive, one's in the negative, and mathematically the output is always negative. But two wrongs make a right. So in the last, from 270 to 360 degrees of rotation there, uh, we are putting in power from the applied source to create a magnetic field in the inductor, and the product of two negatives is a positive. So that's why I joke that two wrongs make a right in this case. So uh, in that last, quarter of the cycle, again, voltage and current are both in the negative. So in the blue, portions of this 360 degrees of rotation, we're getting power out in the form of a magnetic field. So we're creating a magnetic field. But from 0 to 90, and then again from 180 to 270, that magnetic field we've created is now collapsing, and it's actually returning power back to the source. So again, it's just now, from 0 to 90, Luke Wilson gives Will Ferrell the bread maker, and from 90 to 180, Will Ferrell gives it back. And that relationship just continues to go on in a purely inductive or a purely capacitive circuit. And capacitive just being, well, we put in power to create an electrostatic field. Electrostatic field is displaced and returned to the source with a counter electromotive force.
So that puts me to sleep,
Yeah.
and I don't know what you just said, but but the way I explain this, and tell me if this is way too elementary. I explain this almost like a sound wave echo. If I were to put a bunch of power into an inductor, like a transformer, let's say, it's going to more or less shout right back at me. All the power that I've put into it is going to come back at me because I am creating little magnetic waves, little in every turn of that transformer. So it's going to end up just coming right back at me. So almost like a feedback loop.
Yeah, I like that analogy. Yeah.
So if
That
I
might be
so
even better for like resonant frequencies and tank circuits and figuring out circulating currents, but that's like way beyond us.
it's beyond me.
But yeah, I like that analogy. Yeah.
I know it's not 100% accurate, but I'm trying to put myself in the position of a second year apprentice. All these concepts, even this language and verbiage, is brand new to me. So if I
Mm-hmm.
were to just boil it down to the brass tacks, I've got voltage coming back at me. I can
Mm-hmm.
explain to most guys who've gone through a first year apprenticeship why a light bulb doesn't trip a breaker.
Sure.
Because I could say that a light bulb doesn't trip a breaker because the resistance is increased and therefore my current is decreased.
Mm-hmm.
So ultimately, what all this stuff does is it creates all these magnetic fields that act like
Uh,
resistance,
yeah, in the form of opposition to current flow.
right? And
Yeah.
therefore allow me to lower my current because my resistance, my opposition to current flow, it acts like resistance, and therefore the same as a light bulb doesn't trip off a breaker. My transformer won't trip off a breaker because it has some type of impedance lowering the current.
Yeah, overall circuit impedance. So yeah, it can be a struggle, I guess, when you really break it down into one rotation, what's going on. But that's why I like the regift analogy. That you look at this and mathematically, the product of two positives is a positive, the product of two negatives is a positive, but the product of a positive and negative is a negative. So it's either, the yin and the yang, that half the time it's the inductor giving power back to the source, and the other half of the cycle, it's the source giving power back to the inductor. And then to really break it down is, well, an inductor, like a coil of wire is an inductor. And there's so much wound equipment out there that would describe a good inductor. Wound equipment, single wire, wrapped a lot, right? So what are some of the things we can think about? That's an inductor, a transformer, a motor, an arc welder, phase converters, a lot of just wound equipment. But basically, you put power in to create a magnetic field. That's ultimately that's what we need, right? That's the main operating principle of a transformer. I got to have an operating field. Um, Induction motors, AC motors. I got to create a magnetic field, but you create the magnetic field, but alternating currents constantly changing magnitude, right? Not magnitude, direction. It's constantly changing direction. So it changes direction, and that field you created now collapses, and the collapsing field, induces a counter electromotive force. That's an opposition to current flow. That's
Which is
that
why my voltage and current are 90 degrees here.
Yeah,
When my
and what's
current's at
not
the lowest, my voltage is at its highest.
well, and that's the applied voltage. But so yeah, if you looked at the 90-degree portion of this sine wave, if you were to draw in the voltage induced by the collapsing field, that's what we call counter electromotive force. It's 180 degrees out of phase with the applied. And it reaches its peak at 90 degrees because that's when the current escalates to its zero, like goes downhill to its zero value. That's the greatest rate of change. So at the greatest rate of change is when I get the highest CEMF. So at that
So
zero
I would
value,
actually
that's
be like this.
correct. So you reach your peak CEMF value at 90 and 270, and you can see that the current's actually at zero. That's when, so at the peak current point, we've put in the power to create the greatest magnetic field we can. There it is. We've achieved it. That's as strong as the magnetic field's going to get, right? And now we change direction. The magnetic field, we put all that work in, and that magnetic field we created collapses. As it collapses, it puts that up, counter electromotive force there in the blue, and it reaches its peak value when the current collapses at zero. That's when the speed of the cutting actually, the most magnetic lines of flux are cutting into the coils, the applied circuit conductors. So, and that's an opposing force. They're 180 degrees out of phase with each other. And it's just like, line 1, line 2 in a single phase 120, 240. Well, at the neutral point, what's the potential? There isn't one, right? Because I've got two equal opposing forces, that merging right there. So I've used before, like, if the fire department were to hook up a hose, but then at the end of the hose, there's just another fire department hooking up another hose that in opposition, there's two different, flows of water running in opposition to each other. That's like, a reactive component.
All right. So this counter electric CEMF. Boy, I can't speak today. So let's stick with the acronyms. And the applied voltage being totally out of phase, it more or less, to me, acts. It's a form of impedance, opposition to current flow, and this is the basics of it.
Mm-hmm.
So, how does this help me to understand power factor? Why do I need to know this to actually understand power factor?
That's a question I always struggle with, right? What's the practical application? It's out there, it's real. As we continue to get more involved with energy studies, right, or energy efficiencies and energy codes, more people should be aware of this. That a lot of the energy codes always refer to wattage, and it just infuriates me, and I imagine others who know the difference. That you could have a lamp that's of low wattage, but it might have a really poor power factor. Where we all know, hold on, the VA value really isn't all that good because the efficiency is really poor, and all you're worried about is the wattage. Well, the reality is how much current's being put on those transmission lines. That's VA. That's the apparent power. We call it apparent power, but you don't get something for nothing, right? You have to put in. The voltage is fixed. Utility does a good job keeping voltages where they need to be, so we're always just going to use nominal voltages. Everything's perfect. Well, I got to put in so much current to get a certain amount of wattage out because that's the reality. If I use these measuring devices and I see, man, these transmission lines are really carrying a lot of current, but the reality is we're only getting this much true power out. That's not good for anybody, right? So even the utility wants you, encourage you to have, better power factors in your commercial facilities, and they do that. You're not, you're not paying for power in kilowatt hours, you're paying it in kVA hours. So you're encouraged to, you know, have a better power factor. It decreases your bill. So the end user, you decrease your bill, but everyone's happy because we don't have to put in as much power either.
Okay, so let me get this straight. I want to know about power factor at the end of the day. This is where the rubber meets the road. I have
Mm-hmm.
I have apparent power, I have reactive power, and I have true power.
Mm-hmm.
So my true power is there's a wheelbarrow analogy, right? So if I'm moving bricks in a wheelbarrow, I still have to lift up and use power to lift up the back end of the wheelbarrow.
Mm-hmm.
I'm not going anywhere. I'm not getting anything accomplished, but I have to spend that energy to lift up the wheelbarrow.
Okay, I like that.
I want to go forward. Now I get true power. That's truly going forward by pushing forward, but I have to actually do the lifting in order to do the pushing.
Mm-hmm.
Otherwise, I'm never going to get it done. So I like the wheelbarrow mode, or so that's the way I look at it. So if I have real true power, how does this affect? I guess that's my question. I'm a second year apprentice here. I have apparent power, reactive power, and true power. My power factor is the ratio of the true power to apparent power.
Mm-hmm. Yeah,
So
so this one could be better, right? So you put the little number on top of the big number because number one, the best you can ever do is 100%. So it's that would be false to say you can get more true power than you can apparent power. So to keep things simple, it's always the little number on top of the big number. So power factor is just that ratio. I'm comparing true power as compared to apparent power. It's going to result in a decimal fraction. And when multiplied by 100, that's what we determine, well, how good is your power factor, right?
so let me get this straight. In this case,
Mm-hmm.
and we have another slide that's going to give us our angle theta here, but so in this case, I'm going to go 691,
Mm-hmm.
and I'm gonna divide 1152 by 691.
Yeah.
And so I have a. Do you have a calculator with you?
Yeah, but I don't know how to use it.
Well, I don't either. That's why I was hoping you had it. It was an excuse.
I've
It was
got
an
one.
excuse so you
We
wouldn't
can make
use it.
sure we both get the same, I guess.
Yeah.
All right. So I've got really impressive power factor, 60%. Is that what you're getting?
Yeah.
0.59 repeating, roughly.
Yeah, that isn't good. So if I have 152 divided by 691,
Mm-hmm.
I'm getting 1.6.
Huh? You
Yeah,
put the big number on top.
didn't I? Oh man. See, I told you I didn't know how to use it.
See, good thing we're both here. Yeah.
Yeah. Whew.
You got a really awesome power factor.
So I've got 0.59
Yeah.
is my power factor. So what do I do with that decimal now?
Well, you can multiply by 100, right? To figure out that's your percentage power factor. I mean, so the closer we get to 100, that's the most desirable. So you got 59% power factor, which would be considered by most, I'm sure, to be undesirable, not where you'd like to be at.
So let me get this straight. If I'm getting charged for the full beer,
Mm-hmm.
you're telling me that this beer is 60% foam? 59% foam?
41%. 41% foam.
41% foam,
You like that?
59% beer. Yeah.
That would be your reactive component of it. Yeah, you're getting 41% foam.
So who wants to pay for a $150 beer and get 41% foam?
Not many.
No.
Just like the commercial facility with the poor power factor, not a lot to be desired there.
Right. Okay, cool. So I'm getting 41% foam in my beer. That's a really, really nice. Okay, so now angle theta. Who
Yeah.
cares? What? I don't get it. What's the deal? Why do I need to
So
know this?
why am I worried about angle theta? So angle theta, that would be would correspond to, okay, if you had your calculator and you hit cosine, and we're going to use cosine because I'm comparing. So if I took a dissecting line through the angle theta, right? I'm using the trigonometric function cosine because I'm given my adjacent in true power.
So if
Also my
I would say this is adjacent. Oh
No,
wait, no,
that
this
would
is
be
my
the
adjacent.
opposite. Yeah, so adjacent's given in true power, and the hypotenuse is given in apparent power. So, yeah, why am I looking at the cosine? Because we just determined, well, power factor is adjacent over hypotenuse, right? So Oscar had a heap of apples, or SOHCAHTOA. That's why we're looking at the cosine here. And why do I care about the angle theta? The angle theta, if I were to punch in 0.599 inverse cosine, I'd find that voltage and current are 53 degrees out of whack with each other, right? We got to find some more bipartisanship between voltage and current here. How could we do that? So we determined we got 59% power factor. So if I take the inverse of 0.599, that's where I'm going to find 53.13. I can double check that.
I did.
Okay.
So then I hit cosine minus 1,
Yeah.
and that equals 53.13.
Okay. So we know that what's a way to correct this? We know why we're worried about correcting it, right? I want less foam in the beer. Well, is there a way to shorten the hypotenuse? Could I do that? Right?
I just need to shoot for a lower angle.
Yeah, I could do that because inductive components and capacitive components are
Totally opposite of one another. So
totally
if I
opposite.
had, so you're telling me, Eli the Iceman.
Yeah, so if it was my voltage leading the current by 53 degrees, well, I may be able to add a capacitive bank here, reduce the amount of inductance because vectorially the way inductors and capacitors add, at least X of L, X of C, whatever reactive powers, because they're 180 degrees apart, it's just easier to say I take the difference, right? I just subtract them. That's how they're going to add vectorially anyways, because they're 180 degrees apart. I just take the difference.
So Eli the Iceman is what we
Chuck's
use.
brother, Liddell.
Chuck Liddell's brother. Okay, all right.
Yeah, the Ice family.
So just to draw this out to give
Vanilla,
myself
Chuck, and Eli.
a visual. I don't know what you're talking about. I don't condone violence or any of that fighting
Well,
stuff.
Vanilla Ice, I guess. All right, we could say he's violent. I'm
I'm
always
just
dating
kidding.
myself. Yeah.
I don't know anything about UFC fights. But so if I was to draw this, what you're saying is if I had voltage in a purely inductive circuit, and the blue line is my voltage,
Mm-hmm.
then you're saying that my current would actually be lagging by 90 degrees, up to 90 degrees.
Maximum. Yeah, we've already established that's the maximum, right? That's why Pythagorean theorem works so well for AC theory, because That's the maximum phase angle displacement we can have. I'm happy you're drawing this. I never do that correctly.
Right. So I
Right.
would have my voltage being the light blue line
Mm.
and my current being the darker line here.
Mm-hmm.
And that would be a purely inductive circuit. So
Yep.
what you're telling me now is if I were to do the same thing for a purely capacitive circuit,
Oh, I
that
like
I
where you're going. See, I've never shown it like this before.
you 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 so
I
I'm
haven't.
okay.
Yeah.
So I would say the dark blue line now would be my current still.
Okay.
And the light blue line would be now my voltage. Same
Yep.
thing. So what you're telling me is if I were to put an inductor and a capacitor of equal
Reactances.
impedance,
Mm.
reactance, there you go,
Mm.
of equal reactance together, I would actually be able to take this red line of my hypotenuse and shoot it at a lower angle
Yeah.
because I would get less reactive power overall.
Yeah. Like this song, X of L and X of C meet together in perfect harmony.
I love that song. Is that the Carpenters?
Maybe, yeah.
Okay.
But either way, yeah.
All right.
So,
Yeah.
yeah, because they're 180 degrees out of whack, we can look at scalars, we can add these vectorially, but it's the difference. So picture just 180 degrees in the opposite direction of my vars. If I added some more capacitance, well, that would be an arrow going down, right? So that's how they're going to add vectorially. I subtract the little one from the big one. Yeah, and maybe you got a few caps in parallel.
So that's going to drag this down here, and it's
Yep,
going to ultimately make my angle theta
less.
much less,
Yeah, which is more desirable, right? So,
which is a better power factor. Because the closer I get to true power, the less foam I have in my beer.
yep, yeah. So,
Man,
100% power, cosine of the angle, 0, right?
wow. It really doesn't pay to be stupid. Yeah, it took me a while to get this. So I really appreciate you going over this. I think a lot of people that are struggling with the concept, whenever
Yeah, benefit.
I kind of gotta put an anchor on you and slow
I
you
know.
down, and
Yeah.
then you can explain it to them better.
Yeah.
So here we go. So we're talking about RLC series circuits. Now we throw that term around. We're talking about what? Purely resistive circuit, or purely just a resistor like
A
a
lamp.
light bulb,
Yeah. Or,
old
I
school
mean, a
light bulb.
heater, right? There's your space heater,
Okay, I got a space heater, and now I've got a
exhaust fan.
transformer, a fan motor. Okay,
Yeah.
some kind of wound coiled product,
Yeah.
and then I have a capacitor.
Yeah.
So you're going to tell me that my RLC is going to be resistive, inductive, and capacitive
Capacitive. Yeah.
circuit in a series.
Mm-hmm.
Those just add together, right? I mean,
Vectorially.
right? Oh, vectorially.
They do just add together.
Dang it.
So,
So I
yeah.
can't. So this isn't like first year DC current. I can't just say if I'm looking for my voltage here, it's going to be the same everywhere. Or my impedance here is not going to be the same. I don't just add my
So,
resistance here is
yeah,
3.
yeah,
My
those simple rules still apply though, right? I mean, what's the current at each component? It's equal. That
in a
doesn't
series
change, right?
circuit.
There's only one path for current to flow. It's forced to go through all three of those components. It'll be equal at all three. But is it as easy as going, well, RT is equal to R1 plus R2 plus R3? That still holds true as well, but you got to bring in the Pythagorean theorem, right? Is these that no longer is the resistance or the total opposition, whether it be an impedance because we've got reactance and resistance now. Yeah, they just add together in series, but they need to be added vectorially. They're going
Okay.
different directions.
So you got ahead of me on the current. I wasn't asking you about current. I was
Yeah,
trying to
sorry.
give you everything but current on this
Yeah,
series.
yeah. But so RT plus R1 plus R2 plus R still works, right? I mean, those fundamental principles or rules of a series circuit, they're still there, but you can't simply add them.
They
So
just
again,
don't work. Let me get this straight and try and. I know I'm slowing you down and you're just dying to get into some math. I know you.
yeah,
I know. So let me just talk without math. Because the situation we had on the last slide, on the previous slide, where we have current and voltage out of phase, like in these two, and I could have an inductor with half the reactance of this
cap.
uh, this capacitor. And so
Mm,
what I'm doing is I have my angle theta getting reduced, right?
mm-hmm,
But but it's not a straight reduction. I can't do my straight math anymore
mm-hmm,
because because let's say my my capacitor only has half of the reactance that my inductor does. I'm not bringing that arrow all the way down. I'm only bringing it down a degree, a
mm-hmm.
percentage. So I can't just add straight across, right? So now I
Correct.
have to use different math. And that's what's really screwing me up on all this, right? I mean, does that make sense?
Yeah, yeah. And but you and I know. I was lucky enough. My second year instructor, right, Cal Blair, and I never forgot. There is a way to make this really easy, right?
Pray
So
tell, what is
what you and I now call, because we just snaked it from Cal Blair, columns and rows, and how to solve for a row versus a column. And the row is the only time an apprentice will have any difficulty, because we're under the assumption that they've got basic series, parallel, and combination circuit solving figured out for DC circuits or AC circuits with only resistive components. Uh, that said, columns and rows, the total is always the hypotenuse, and a row has to be solved vectorially. They're in different directions. Well, I just referred to one being the hypotenuse, right? What's the furthest we can get voltage and current out of phase with each other? 90 degrees. So it's as
that?
simple as a squared plus b squared equals c squared.
And you're talking about Cal with the columns and rows because I have every intent on stealing his idea and giving it away here. But
Yeah.
the way I got it, I know he was your second year instructor, but I got it when I think my first year teaching, second year, I asked Cal to explain it, and then I recorded a video of him while he was on a whiteboard, and I
Mm-hmm.
watched it about 14 times.
Yep.
And about the 17th time, it made a whole lot of
It
sense.
clicked. I got it.
I was
Yeah.
like, oh man, this is just, I've been really dumb. Because do you want to get into that? We could do that. Do you want to do total impedance in a series circuit and go through this? We kind of went through the vector math a little bit here, right?
Yeah, we can just solve a circuit. Yeah.
You want to just solve a circuit? So 180 degrees is what you're talking about. We have to use vector math to get there.
Yeah,
Because it's
which,
not
I mean, how do those reactances add? They add vectorially, or they're 180 degrees apart. It, it's the difference. Subtract the little from the big. Simple.
and two negatives equal a positive.
Yeah, two wrongs make a right.
It's fantastic.
For power factor, yeah.
It's super
Oh, the
easy.
product of two negatives, right? Multiply a negative by a negative. Happy time,
Right.
right? Okay.
So here we are. What do we have? We have
Yeah, and so for
impedance.
columns and rows, you'd have to just kind of I know a lot of instructors also refer to this as like, well, let's table these values, let's put them in a spreadsheet. So I take all my E values, what's the applied or total voltage, what's the volt drops across the resistive component, the inductive component, the capacitive component, and that's how we form a row. Right, so like the slide you have, you'd have to kind of take all those values in the cap, and you'd have to slide it just to the right of the inductor, right? So I'd have volts dropped across the capacitor, what's the current flow through the capacitor, uh, what's the total reactance of the capacitor, what's the reactive power, or the VARs of C, and we usually just don't solve for the capacitance.
So if I
We
were to do
can, but
that, I don't know if I have enough room here. Probably not. So you're saying then I could do my current the same way?
yeah, or if you can write really small, or can you just blow this image up? And
Not very well, no.
okay, but
But if I
I'm
did,
picturing like you just writing, uh, and I can't write on here, huh?
not
Yeah,
really.
you're right. And you can't see my cursor.
Nope.
Uh,
It's just another way I have to control you.
yeah, but that's fine. Uh, if you were
If I
just
did,
to take those values at the cap and put them to the right of the inductor ones. I mean, so we can physically see the circuit, right? It's the resistor, the inductor, and the capacitor in series. We get that. And we've got some values given to us, and we're going to solve.
so like this. So when we're talking about columns and rows, we're literally going to turn this into like a little Sudoku puzzle, right?
Yeah.
So my total VA, which is something we didn't really touch on, but so my VA, let's call that what, power, and then VARs of C,
Yep.
VARs of L,
Mm-hmm.
and then do we want to do power factor and angle theta?
We can do that. Yeah.
Is that it?
That's
So
it.
I've got. So you're telling me that I've got 4 columns, and in most of my columns I've only got 4. Am I missing something?
No, you got it. So, yeah, and the way that columns and rows works is that if you've got any two values in a column, you can just apply Ohm's law and solve for all the remaining,
So
right?
if I have 2 values in a column in a row,
Yep.
so if I have 2 values in a row or a column,
Column.
and how many in a row?
All but one.
3 values in a row.
Yeah, unless you've got more components.
Okay, so in this example, let's just use the math that they already have up, right? So if I have resistance of 12,
Mm-hmm.
I have X of L is 24. Let me
Yep.
change my colors just so that we're dealing with. Oops.
Well, and it's already solved on there. I mean, so yeah, we'll have to give it a voltage or something,
Right.
applied voltage to solve for the rest of it. But
Right. So if my resistance is 12, though,
yep,
my X of C here,
8,
8, and my X of L is
24.
24.
Yeah,
And the way they got there was
a squared plus b squared equals c squared. That so one other rule just to remember or note to write down that makes it easy is all of those totals, Z, VA, total current, total voltage are the hypotenuse, right? So it's always the legs are the resistive and reactive components that form that right triangle.
So here's my right triangle.
Yeah, so every total. So our total now, the only row we can solve for, because we've got all values but one, are the total opposition to current flow in the AC circuit, which is the impedance, right? So how do those resistive and reactive components add together?
So you're
What's the
saying my a squared, b squared, c squared. Where do I? So how does this work according to this, the last slide? So if I have my hypotenuse here, what's my hypotenuse?
impedance?
My total impedance.
Mm-hmm.
Okay, so what's my adjacent?
Well, now we'd be looking at a different angle there,
Mm-hmm.
but because the last slide, our adjacent was the resistive leg, where the opposite is.
Oh,
But
you do that.
yeah, so
Tell me where to put it. How about that?
an easy way to think of it is with the right triangle, because if you do much vectors right, you start with a horizontal line, and that's a 0 degree, and we know that voltage and current, there's always in phase through resistance, so that's my 0 degree,
This one
right?
here.
Yep. So that's always going to be the resistive part of the right triangle. R.
Okay.
Yep. And then on the left is always going to be the reactive components, or the X. And I just leave it as X.
So you want me to
I
draw
don't,
a hypotenuse as an X?
Z. So the hypotenuse will be the Z. Yep. So that would be the X. And, total distance between those two that can possibly be heading in the same magnitude or different magnitudes, but different directions, and the most they can ever be separated is 90 degrees. That's why Pythagorean theorem just works for these formulas, is 90 degrees. So, and the totals are always the hypotenuse. So to make it really easy, there we go. Well, I just put, different values in here, but if I told you, well, how would I solve for that hypotenuse? I've given you the two legs that form the right triangle. How would I solve for the hypotenuse? That's as simple as a squared plus b squared equals c squared. So that's what we're going to do. But the problem is I don't know how much reactance I have right now, right? So step one, we said columns and rows. Columns and rows is easy, but step one's always going to be determine what's the difference between capacitive reactance and inductive reactance.
So I need to figure this out here before I can actually give this a number. Is that what you're telling me?
Yeah. So how do those add vectorially? Well, we take the little from the big. That's how they're always going to add vectorially, 180 degrees apart. So whether you want to earmuff that as an apprentice and go, I don't like the add vectorially, right? It makes my head hurt. Find the difference. What's the difference? And
So
even if it results in a negative number, you're always going to square it. And that's going to be a positive. So, but the difference between 8 and 24 are 16.
So I would literally go over to this table, and this is the way I've always done it in my class.
Okay, I like that.
I draw
Step
the
one.
parentheses in the columns and rows.
Mm-hmm.
I do my 8 from my 24. I'm going to square it, therefore it cannot ever be a negative number.
Mm-hmm.
Right? Doesn't really matter. So I have 16. And this is now what this is supposed to represent. So now I have a number I could put into X over here, right?
Mm-hmm. Booyah.
Does that work for you?
Yeah, that's it.
16. So now I take this, I go to 16. So now I know that my total vectorial sum, am I using the right word here?
Mm-hmm.
For
Mm-hmm.
my 8 and 24 is 16. So
Mm-hmm.
now I have that number. I have to go to the next step of this, which is basically the square root of 12 squared plus my 16.
Mm-hmm.
So now I just do 12 squared,
Mm-hmm.
which is what?
144.
44. And then 16
250,
squared.
256.
So I could just do a squared plus b squared equals.
400.
Is that what that is?
No, that's a squared plus b squared. And then, I mean, to get c squared, well, you got to take the square root of 400.
So I take my 144 plus my 256,
Yep.
and I get 400. And now I just get the square root of 400,
Yeah.
and I get
20.
20.
Mm-hmm.
So now that's how I got to 20.
Yeah. And then, we could solve the rest. If we were to give it like a voltage value and say, we applied 97 volts, nominal. Pretty typical voltage
So,
system.
but before I get into that, I have a question for you.
Mm-hmm.
That same exact math works in a series circuit on current and VA.
Yeah.
I use the right angle math. So if I were to be given only
Current.
current, I should be able to do the same thing exactly, right? I would
Yeah.
have another hypotenuse.
Perfect. Yeah. Plus, actually, it makes it easier that any row is going to be, we'll solve for that row with a squared plus b squared equals c squared. Or if you're given the total current, but you don't know how much current flows to the resistor, well, then it's going to be c squared minus b squared equals a squared. And that works for either series or parallel. That's the way. If it's a row, it's Pythagorean theorem.
If it's a
Minus
column, what can I use?
parallel. If it's a column, we just simply use Ohm's law. But we
Ohm's
can't solve anything more because we just weren't given enough. But let's say
Well,
we measured
let's say that
97
we're at
volts at the source.
277 volts.
277. Okay.
Now I have.
We have two values in the column. We can solve the remaining.
So now if I want to know my current, I just use Ohm's law.
Yes, voltage over resistance, which in this case, total opposition's impedance. So even though it's shown by a letter Z, still measured in ohms, total opposition, like resistance, is 277 over 20. I don't know what that gives me.
13.8.
13.8. Okay.
And if I wanted to know what my power, my VA, my volt
Yep.
amp,
Volts times amps. 277 times 13.8. So just Ohm's law now, I get 3,823.
man, and I can do that on every column and every row. And there's
Yeah.
nothing. So what you're telling me is there's not a single thing in a RLC circuit in a series that I can't solve this way.
No. In series, I like that you say in series because adding the resistor is a little bit more tricky. In parallel, just a longer formula. But if you're given, values in a row for a parallel circuit, where you've got all the values but one, and you've got, either the current or the power, again, that's simple. If it's a row, it's right triangle math. Works for
Okay.
everything other than resistance. But again, that just goes back to some of the fundamentals that, that overall or total opposition in any parallel circuit is actually less than, the lowest either resistor or reactive component. So, you know, like adding a lane to the highway, right? That even though you're adding more branches or nodes for total current flow, each branch or node you add reduces the overall opposition. So I always did, if traffic's bad, well, the equivalency would be, yeah, I'm going to put another inductor in parallel, but basically, the amount of electrons flowing, same as the cars on the highway. If you add another lane,
So, do you have time to do a series, a rows and columns on a series and parallel?
Yeah.
Okay. Do you want to finish this one?
If we can
Go
get through it quickly.
all the way through power factor? Do you want, if you want, you got your calculator?
Yeah.
You
Ready?
want to do this one real quick?
Yeah.
All right.
So
So I
the
know that
only
I
way
have.
to solve for the remaining of these, the current at each component is equal here. So
Did I
that
get
doesn't
that
change
correct
either.
before we even get?
We'll
Did I?
find out. We can
Oh
add
yeah.
the volts dropped. We can do some Kirchhoff law and figure out, did we do this correctly?
It's better than
So,
Linz's law because he's the jerk that made me do all this right triangle math to begin with.
yeah, so 12 times 13.8, 165.6 volts dropped across the resistor,
I'm sorry. Say that again.
165.5. Yeah,
Okay.
and 13.8 current times inductive or capacitive reactance, gives me 110.4 drop. Not the power. Sorry, I was just solving all the volts.
Oh,
My bad.
that's okay. So I can easily go there. 110.4 on my capacitor. Voltage across
Yeah,
the capacitor. Okay.
yeah.
And my voltage across the inductor.
13.8 times
Oops.
24, 331.2.
331.2.
Mm-hmm.
Perfect.
Okay. True power, 165.5 volts times 13.8 amperes of current, 2,284.
Wow.
And reactive power as far as a C, 110.4 times 13.8, 1,524. And 331.2 times 13.8, 4,571.
Fantastic.
Okay,
Now, how
power
do I figure
factor.
out
That's we're just comparing true power,
the
watts
VA?
or P,
Yeah.
over the apparent. Yeah, so
So P over
2,000.
VA.
Yep, 2,284 as compared to 3,823. 60%. So 0.6. I'm doing some rounding, but yeah, 60%.
So do I do cosine or cosine minus 1 if I have a decimal to figure out
Yeah,
my
so
angle theta?
anytime you got a decimal, you want to inverse the trigonometric function. So I'm going to go, second or arc sine or the arrow up, and then I should have cosine to the -1, the inverse cosine, punch in 0.6, 53 degrees is the phase angle separation between voltage and current.
Another really bad. Well, I guess this is the same.
Yeah, so
Oh,
it's pretty
it's the
close.
same as
Yeah,
we did before. Yeah. Okay.
yeah. So voltage is leading the current by 53 degrees.
Okay. So there we have it. So we just solved everything for a series.
Yep.
And I think we got a lot of rules down. So if I uh, have a decimal, then I use my cosine minus 1. If it comes out not as a decimal, as a whole number, I just use cosine.
Mm-hmm. Yeah, like so if you were asked if I gave you the angle theta, 53 degrees, and asked you what's the power factor? Well, the 53 degrees is your whole number, so there's no more inverse because I gave you a whole number. You just punch in cosine 53, and you're going to find it's 60.6. So you can solve your power factor if you're given uh, the
Angle
angle
theta.
theta. Yeah.
By hitting the cosine button gives you the power factor.
Yeah.
Okay. All right. Just wanted to go through that so we're all on the same page.
Yeah, that'll be good too. Yeah.
Okay. And then, so we'll just try and get through this because I know we don't have unlimited time here. But so now we're talking about a parallel circuit.
Mm-hmm.
All right. So without spending much time on this, we all know what a parallel circuit is. We've already gone over what our RLC stands for. So without further ado, we now have an
Look at that.
RLC circuit
Yeah.
in parallel. Now what do I do? Everything's different.
Do any more values go in there, or we just start adding our own?
No, I'm just gonna make up my own. Let's see how bad I can screw this up. Do you want me to draw another?
I think you should give us the current drops, or how much current flows through each component, just to make it easier for now.
Okay, so let's just. Should I draw the columns and rows like we did on the last one, just so we're looking
Yeah,
at
you
apples
can.
and apples?
Yeah. Go ahead.
Okay, so let me just do this. If I have my volt total, my current total, my impedance total, my VA total, my power factor, and my angle theta.
Mm-hmm.
I'm going to try to draw this as square as I can while still being somewhat in a hurry here. So now I could take my resistance. My capacitive voltage, my capacitive current, my capacitive reactance, my VARs of L, if I took my, oh, I said capacitive, I meant inductive. That's a capital I, X of C, and my VARs C. So I don't know if you caught that, but I had my capacitive and my inductive a little bit backwards. You want me to give you current?
Yeah, that'd be easier.
So
We can go over the formula at another time for RLC parallel circuits for total impedance. How do you solve?
Okay, so you want me to give you current across the whole thing?
Yeah.
What are you thinking? Total current?
We can do total current. Let's do, I like 16 amperes of current flowing. We'll do 8 of those. In the 8 amperes of current flow through the inductor, and 5 through the capacitor. There we go. And voltage applied.
What do you want to do? 120?
Sure. Whatever it takes.
121?
Yeah.
Okay.
Okay. So simple.
So in a parallel circuit, is my voltage the same at all points?
Yeah, so you can do that too. You can cheat. And you can only use columns here if you wanted to. Well, minus one column, right?
Well,
We're kind of stuck with one column there. So we can cheat, but we're going to have to solve how much current's flowing through the resistor. How do we do that? I've only got one value in that column, in the resistance column. So, well,
so where do I start?
they just simply add up, right? You remember the good old days where voltage and current were in phase? They just add up.
So what if I put 3 here?
Yeah, they don't add up here, right? So,
Oh, I can't do that?
yeah, that it would,
Oh.
yeah. Again, if I want to solve for the current drop or current flow through the resistor, it's 16 squared minus 3 squared and the square root of that. And so the reason we're coming up with that is because the total current is the hypotenuse, or C, right? So the formula, A squared plus B squared equals C squared, or if we want to solve for A squared, we can take C squared minus B squared. So, and Tom, like you did in the parentheses, that this is a row. To solve a row, we have to do right triangle math. But before we do the right triangle math, we got to vectorially add the current drops through the inductor and the capacitor. They're 180 degrees.
So tell me how do I draw in my current here? So I want to figure this out. I have 8, I have 5, I have 16. Where do I start?
We got to take the difference between
So
inductance and capacitance.
so I'm going to do this. I'm going to do this right here, and then I subtract this
Subtract.
and then square it.
Yeah.
So I take my 3.
Mm-hmm. Yep. So now we've solved for the vertical leg of the right triangle.
So that's 3.
Yep. We were given the hypotenuse is 16. Now we got to solve for the resistance.
So I do that with what formula again? Is this what I do?
A squared is equal to C squared minus B squared.
Three?
Yep. Yep. So we know 16 squared is 156, if memory serves me the last time we did it. 256. Yep. 3 squared is 9.
Is what, 9?
Yeah.
Okay.
And the difference is 247. And I gotta take the square root of 247, which is 15.7.
So my resistance here is 15.7?
Mm-hmm.
All right.
And now it's just columns.
Same thing.
Mm-hmm.
So when do I use the inverse function?
So another way to do this easily, yeah, because that's always an issue in homework is if you're using the inverse trigonometric function, it's because you've been given a decimal. If it's a whole number, you don't inverse the trigonometric function. So another way to look at that is the power factor is always given in a decimal, and then we convert it to the percentage, right? So if I'm going from power factor to angle theta, it's inverse cosine. If I'm going from angle theta to power factor, it's cosine.
Gotcha.
Mm-hmm.
Okay, so now we just do. I got 120 volts and 16 amps. What's my VA or resistance?
1 second. Now I got my wife calling me. She would love to be here
Oh
talking
man,
power factors.
again with they're always
Yeah,
they're always
so
doing that. If it's not my wife,
16
16 VA.
times
Oh,
120, 1,920.
okay. And I'm just writing down what you're saying. So I assume that was the VA.
Yes, it was. Yeah.
Okay.
So yeah, now we can solve for uh, total impedance here by taking the VA. Sorry, I'm going to just multiply or take the voltage over the current. Texting with my wife now. This is good. 7.5 ohms of impedance.
7.5.
Okay. Yeah, and I'm back. We're good. So, all right, here we
Okay.
go. All right.
If I had a dollar every time my wife was bugging me about power factor.
Total resistance 120 volts over 15.7 amperes of current, or the resistance 7.64. And the power here, 120 times 15.7. Whoa. 1,884. All right. 120 volts across the inductor divided by 8 amperes of current is 15 ohms of inductive reactance. And 120 volts times 8 amps, 960 bars of L. All right, 120 volts drop, 5 amperes of current flowing, 24 ohms of capacitive reactance. And 5 times 120, 600 volt amperes reactive in the capacitor.
So now if I want to figure out what my power factor is, I take my VA over my power.
Yeah, or if we want to double check that we got all those values correct, we can go, hey, is VA equal to power squared plus vars of L minus vars of C squared?
All
So
right, so
just a way to
power
double
squared
check ourselves.
is 1884
Mm-hmm.
squared. And you
Uh,
said vars of L what?
we got to find the difference first always. So because they're 180 degrees out of whack, we always just subtract them so they don't. The way they add vectorially is just the difference. So we're left with 360 to square. But you want that number first a little smaller.
What?
So 360 squared is 129,600. And the power squared is 3,549,456. There we
And,
go.
and and I just subtract these.
We're going to add those.
We're gonna
So now
add
we're
those.
looking for, now we're going to confirm the hypotenuse is 1920.
Oh gosh.
So
So I'm gonna start the first number so you don't have to sweat it. 3 million.
3,679,056.
Okay.
All right. I'm going to take the square root of that. Uh, 1,918.1. Good enough for me. I told you I dropped a lot of decimals out
Mm-hmm.
and rounded pretty quickly with some of these other values. So yeah, double checking
1884.
our yeah, double checking ourselves. We're close. 960 and 600 were there, but a lot of those we got because I dropped other decimal points other places. So
Doesn't really matter. So my
yeah.
power factor in all this. How do you want to do that?
Okay, power factor again, pretty simple. We're just going to solve,
VA.
well, yeah, what's the true power as compared to apparent? Uh, my watts over my VA 1884 over 1920, 98% power factor, 0.98.
So then I take my 0.98 because it's a decimal, and then I
Mm-hmm.
do cosine minus 1,
Mm-hmm.
and that gives me.
11 degrees.
Ooh, that's
11.5 degrees.
that's a pretty good power factor, huh? I mean, compared to what we've been dealing with.
Yeah, a lot closer to zero. Yeah.
Well, I think you've learned a lot today, Chris.
Thank you. Yes.
Yeah.
Appreciate your time.
All right, cool. I think that's good enough for now. If you want to go over that, I think we've given everyone an hour and 22 minutes to think about.
Yeah, or, if you see more things in the chat there, that may be another video.
Yeah, there you go.
Could you do this or that? And the answer will probably be
Of
not
course.
very well, but sure.
Not on my watch.
Yeah.
All right, cool. Well, I will. I'll let you go here, and we'll give everyone something to ponder for the evening, and when they want help sleeping, they can do this.
Yeah. Yeah. There you go.
All right, man.
Good sleep aid. All right.
All right, and we'll talk to you guys later.
See ya.